Welcome to Beyond the Qubit. My guests today are Magdalena and Wolfgang Lechner from Parity Quantum Computing. I'm quite excited to have both today. Parity Quantum Computing is a company that is an expert with smart algorithms and getting more logical qubits out of the qubits. I'm quite keen to learn more about Parity Quantum Computing. And today you had a very important announcement, which I would love to learn more about. So welcome. Before we go into the press release, Magdalena, can you give a short introduction, maximum 2 minutes, why investors should care about Parity?
Sure. Thank you, Frank, for having us. So, as you mentioned, ParityQC is a quantum architecture company. And what this means is that we are not building hardware ourselves, but we are building it together with hardware companies, and they develop the hardware based on our architecture. And why investors should care about this is because developing hardware in the quantum computing world is quite risky, right? We have different modalities, cost lots of money, and what we do is we help quantum hardware companies to benefit from our architecture and leverage this to actually perform world records as we announced earlier, or what we're going to talk about today.
You had an exciting press release today. I want to know more about that, but before we go into this, could you explain the basics of why does Quantum Fourier Transform matter?
Yeah, thank you very much for this question. Today was indeed a great day for ParityQC. We announced the world's largest quantum Fourier transform that was ever performed. And the quantum Fourier transform is not just any algorithm in quantum computing. It is actually the cornerstone of most known quantum algorithms. So there is a so-called quantum algorithm zoo, which is a website that collects all known quantum algorithms at the moment. There are several hundreds of them. And 90% of those that have an exponential speed up are actually based on the quantum Fourier transform. So it's not just an algorithm by itself, but it is more or less the cornerstone of all known quantum algorithms.
Wow, that sounds quite impressive. What is the real technological advance of today? Is it better compilation? Is it better architecture? Is it better hardware, or a combination of all three?
Yeah, it's exactly the combination of the three things that you've... the quantum Fourier transform is studied since the early days of quantum computing. It's because of its importance, it is basically studied since more than 30 years. And the first experimental realizations were in the early 2000s with around 3 qubits. Then, so to say, over the years, people improved this, and I think like 10 years ago or so, we were at the order of 10 qubits where this could have been performed. And very recently, industry kicked in, and companies like IBM, Google, Microsoft, Amazon, and so on started to build quantum computers and made the hardware better. But this hardware improvement alone was not what has led to this world record. Just the hardware improvement itself also grows exponentially, like in Moore's law. But this alone would have not brought us, so to say, to the world record. What really made it the world record was that we combined a new way to implement the quantum Fourier transform. So since 20 years, it was believed that we basically know how the optimal quantum Fourier transform turns out. But actually, we improved this 2 years ago, and we implemented this on the best hardware. So it's really a combination of architecture, hardware, plus compilation.
Okay. And why is the QFT the right benchmark?
Yeah, I think because of the reason that it's used in every known algorithm, it is a benchmark that basically every physicist would agree that this is an important benchmark. Apart from that, from a technical point of view, it is an algorithm where every qubit has to talk with every other qubit at any time. And these all-to-all connected systems are inherently the hardest to compute. And that's why it's a very natural benchmark.
Can you talk us a little bit through how does this bring forward the quantum application use cases?
So, as Wolfgang said, there's SQFT is one of the cornerstones of each algorithm that is known out there in the algorithmic zoo. This also helps bringing quantum computing forward to actually solve applications like drug development or financial modeling or let's say this is not the nicest application of quantum computing, but also cryptography, right? So whatever we do here, so this is why we focused our press release also not on use cases specifically, but showing that this advancement shows that we are actually in the industrialization era of quantum computing, which gives benefits to all these possible applications that we see for quantum computing. And to be honest, 40 or 80 years ago, you wouldn't have imagined what you can do with a classical computer, right? So we are only at the beginning figuring out what quantum computing is really capable of.
Yes. For me personally, what I try to understand is that my timing was somewhere between 2028 and 2030. We could have 100 logical qubits. And then 2035, maybe 1,000, 2,000 logical qubits. And that's when you can really have the ChatGPT moment. That there can be useful applications. But so many things are happening at the moment. It might potentially be accelerated. If we look at the progress of improving logical qubits, like scale up, more qubits per chip or per unit, or scale out, connecting clusters of qubit units, and the physical to logical qubit error ratio, could you quantify a little bit? So how does this breakthrough, how does it accelerate which parts?
Yes, so what we did acts on the logical level, which means we have really achieved 52 data logical qubits. Even though, so to say, in this case, the error correction that we did is not an error correction that we would call a full fault-tolerant error correction. The achievement shows, I think, two things. One is these estimates that you just said. The 2030, we have logical qubits. 2035, we have applications. This seems to really shift now, and more or less in the same weeks, like 2 weeks ago, there were several publications by Google and also others, which actually lowered the estimate from 2035 to 2029, which means we almost halved the time from now on where people like Google expect quantum advantage to happen. And our result goes in the same direction. What we have looked at is the Moore's law of quantum computing, so to say. So what we did was we really looked at, as a function of time, the world record in a full algorithm. So this is not about a KPI like qubits or fidelity or anything, a full algorithm. And we see this doubling, continuing. And if you follow this doubling, then you also reach quantum advantage around the same time, 2030. So this means things seem to agree now, and so to say, looking in the past and looking in the future seems to agree. And that's what we consider as the fundamental contribution of this work, that the Moore's law for quantum computing does not decelerate, it actually accelerates and continues.
Mm-hmm. Okay, thank you for clarifying. How much of the improvement comes from IBM Heron and how much came from parity twine?
So there was, if you look at the results from IBM alone, there was a paper from 3 years ago where 9 qubits was the maximum that could be done fully coherently. Then there was a result by IonQ, which showed 27 qubits. And now, and we have now 52 in the combination of hardware improvement plus the algorithmic improvement. If you would have just the hardware improvement, you would be around 37, which means the improvement that came from the hardware was about factor, 50%, and the doubling, so the other 50% came from the new algorithm.
Okay, that's quite promising. And then the question is, is this technology neutral? So could you apply this only to superconducting or also to other technologies?
Yes, so it's transferable to all platforms that are known.
Why is that? Why is it transferable to other technologies?
So the parity architecture is really a fundamental new way to look at quantum computing. What you typically do if you think about a quantum computer, you translate the bits to the quantum bits and the gates to the quantum gates, and then you make the quantum algorithms. What the problem is then, you need the logistics of the quantum information on your chip. So if two qubits, which are physically distant on your chip, have to interact, they somehow have to be brought together so that they can physically make a gate. The parity architecture works completely different. We have separated the logical information from the qubits. In our case, the translation works like this, that relative information between two logical bits are represented by one physical qubit. So the relative information of two bits becomes one qubit. And mathematically, this is called the parity. So parity means if two bits are the same, it's 1. If two bits are different, it's -1. And this parity information, this is actually then stored on the qubits. And this allows us to abstract the physical distance of qubits from the logical distance of qubits. So we can separate the logistics of the quantum information from the algorithm. And this allows us, for example, to completely avoid swap operations or shuttling operations. And this is something that can be applied and that is useful and can be applied on any platform: superconducting qubits, neutral atoms, ions, NV centers, everything. And then on top of this, at the company, we developed the hardware aspect in more detail. So for example, we have a department in the company that only looks at superconducting qubit, one that only looks at neutral atoms, one that looks at ions, and we even do specialized development for these platforms. So the answer is all platforms benefit, but they benefit in a different way.
Okay, thank you for explaining. There's one part I want to zoom in a little bit more, is on how can you remove the swaps? So what is the technology behind that you don't have to go through that?
So the trick is that if you have this parity information, then a pair interaction, so a gate between qubits, becomes a single qubit operation, because the qubits represent relative information. And this actually allows you to use so usually what you would have some gates, and you would have your swap operations. In our architecture, you can actually use the gates that you do in the algorithm for both, for the algorithm and also for the logistics. And because of this combination, we were able to improve quantum Fourier transform, which was believed for 20 years to be already optimal.
Okay, thank you. When do you say that advantage scales exponentially? And what is the precise comparison baseline?
doubling every constant time. So like Moore's law is doubling every 1.5 years. In quantum, we would have a doubling every 1.5 or 2 years.
And what was the hardest bottleneck that you had to solve, to overcome, to get from 27 to 52 qubits? Was the real challenge routing, calibration noise, compilation complexity, or something else?
So I would say that it's the combination of things again. And it's also not like this that we have started the company and thought, oh, let's beat Quantum Fourier Transform. It was actually, we started from this fundamental transformation, the parity transformation, and we looked at different algorithms. And for the Quantum Fourier Transform, everything beautifully fell into place, right? It's like things that you cannot, decide or make a roadmap or something like this. It's somehow magically everything fits together. And so I would say it was impossible to plan or to figure out which was, so to say, the main bottleneck or the main problem. The parity architecture somehow solved this connectivity problem. This is something that we knew from the beginning, and then we applied it to different algorithms, and somehow, I wouldn't say surprised us, but we were, at least for myself, every time I look at the results, I'm astonished, and it looks like it just came and everything fell into place.
Does this result of the breakthrough, does this change your view of where value will accrue across the value chain? And does it strengthen the case that the architecture and the compilation may become as important as the underlying qubits?
Yeah, for us, I hope it changes the view outside. For us, it never changed the view because we were convinced of this at the start, right? But what it really shows is that hardware alone and software alone doesn't work. So they can't work apart from each other. They have to work together in tandem. And as Wolfgang said, this is also incorporated in our company. So our company not only has algorithmic departments or architecture departments, we really have hardware departments for each platform. So this means that we think from the application to the implementation on the hardware, everything through. So everything has to fit together. And this is what we do with all partners and customers that we work with, is really working hand in hand, as we did with IBM here.
Okay, thank you. That's very helpful. Then a significant part of the podcast is who is behind the management team. Who are the key people who really make a change? And I would like to get to know you a little bit better. Maybe Magdalena, can you start? Can you give a short introduction? What got you into quantum technology, and how did you become the co-founder?
Well, that's a question you have to ask Wolfgang.
Well, let's first go to Wolfgang.
No.
I can tell the story, but it's but it started long before I came into the picture. So when Wolfgang did find this new fundamental way on how to build quantum computers and invented this at the University of Innsbruck, this was when I founded, together with my uncle, another company. And this was one where we fostered spin-outs from the deep tech environment and helped researchers found companies and then also invested in them. And in the course of this, I also got to know Wolfgang, so we've known each other now for over 10 years. I was on the investment side at first when he wanted to spin out the company. It took a long time to spin out the company, but that's also a story that Wolfgang has to tell. And then, briefly before he founded the company, he asked me to switch sides, and this is how I became co-CEO.
And you, Wolfgang, what created your idea that you said, okay, I want to work on this problem?
Yeah, I was a postdoc at the University of Innsbruck working with Peter Zoller. He's a world famous quantum physicist. He was the person who more or less invented the ion-based quantum computers. And this is, of course, an extremely inspiring environment to be in. And for this particular problem, I think I was inspired by the difference between ion-based quantum computers and superconducting-based quantum computers. So this was 2013, and at that time, the problem of connectivity was one which seemed to favor ions quite a lot, because ions were the only ones that were actually able to achieve all-to-all connectivity, while all other platforms were always limited to nearest neighbor interactions. And this was something where I thought, what would actually happen if you would think about it completely differently? And this completely differently was exactly to implement relative information in the qubits instead of the qubit information itself. So this idea to map to relative information and then have local operations that do pair interactions, this was more or less the starting point for everything. And at that time, I was in an office with Philipp Hauke, a good friend of mine, and we basically worked out fundamentals of this idea within, I think, 1 day or 2 days. And then when we looked at the details, I made a mathematical proof that what I had in mind doesn't work. So I could mathematically prove that what I thought was just wrong or too good to be true. And so we forgot about the idea more or less, and we never talked to anybody about this because we thought it was like we were celebrating too early, so to say. And for some reason, and this is the insane part about it. So this was the genius part. Now the insane part about it is that that I still worked on this, even though I myself proved that it doesn't work. And so I secretly worked on this for more than 1.5 years. And then at some point I realized...
What was it that you could not let it go, the idea?
I don't know. I don't know.
Because you continued to work on it.
That's the insane part. It's just the insane part. I cannot explain it. It's... I think it's, I don't know.
Was it feeling that you had the feeling this is the right direction, or?
I didn't even have the feeling that it was the right direction. I cannot control it.
What was then? What caused you then? If you had not the feeling that it was the right direction, but then why did you continue?
Yeah,
did you got energy from it, maybe, or you thought it was fun to work on, or?
Yeah, maybe I wanted to better understand why it didn't work or something like this. I don't know. It's really impossible to explain. But it's not that like I sporadically worked on this. I work quite a lot on this. And what often happens is that with things that you work a lot, that at some point you have it completely in your head. No? So when I found then this what is now called the LHZ construction, which is shown here in the background. So it's basically a setup where you have your parity qubits on the corners, and then these red squares they represent, so to say, the alignment of these qubits. This I basically found at 3 a.m. in bed. So I was waking up, and this came up. And yeah, it was a very crazy experience, I have to say. Because when I had it, I immediately knew that this is super important, and it was also realized then by the community immediately. So we filed a patent, and within half a year, we got an offer for all the IP from one of the tech giants in the US. It was immediately recognized by the community as something that really solves the connectivity problem in a different way than all other solutions.
Okay, can we maybe go into that, but then on a very basic level for the listeners who are not familiar, for investors who are not really into quantum? Can you on a very basic level explain step by step how does the technology work?
So in quantum computing, the big challenge is that other than in normal computers, we cannot copy, delete, and delete information on a chip, but that the information has to be always there. So memory and CPU somehow merge. So that's a fundamental problem in quantum computing that every quantum computer has, which means we cannot do like a bus system and a register system and a memory and a CPU. We have to completely think about it differently. And this is, I would say, something that we are, as a quantum architecture company, are doing uniquely. So this is something that is overlooked by very many, even by the experts. So what we have to achieve is that the information on the chip has to be there all the time, which means we have not just to care about the algorithm, we also have to care about the logistics of the information. And now comes a second problem, which is that quantum information is not just zeros and ones. Actually, the picture that one can have is that you take a sphere like Earth, and the North Pole and the South Pole would be 0 and 1. And the quantum bit can be in any state anywhere on the globe. So you go really from 2 points to the whole surface of Earth. And this also means that quantum information is now something that's more analog than just 0 and 1, which means shifting around information is not just setting something to 0 or 1. It's actually you have to shift around like a lot of information. And this combination makes quantum computing very hard. And at that time when we invented this, the only way to solve this is by so-called swap operations, which means you really move the full information of a qubit around. And now with this parity...
And if you say we move the full information around, do you say we move it to a 0 or a 1, or do you move it to quantum gates?
No,
what
so
do
the problem
exactly
is...
mean with moving the information around?
Yeah, so you
where,
have...
From where to where do you move it?
Yeah. So let's assume you have a chip, and the chip is an array of 10 by 10 qubits. And let's say you have in the top left corner some information, and in the bottom right you have some other information. And now exactly these 2 bits, they have to do an operation. Let's imagine an AND operation. On a classical computer, that's not a big deal. You put both into a register, you do the AND gate, and you put them back. In quantum computing, you cannot do this. The problem is that all information has to be conserved all the time, which means the only thing that you can do is you can move the information from bottom left to top right, or the other way around. Now, this moving is also more complicated than a classical computer because it's not just zeros and ones. What you have to move is like a position on the sphere. So imagine again the North Pole and the South Pole as the bits. The quantum bit actually is any point on Earth. So you basically have to say this qubit is in Vienna, the other one is in Amsterdam, the other one is in New York. And you have to basically then move this information around. And this is very costly. So it's not just copying data around. These are very costly operations. And what the parity architecture does now is it represents everything in relative information. So it means, for example, you would not store the position of Vienna and the position of Amsterdam. You would actually represent everything in relative information. So for example, you store the information of Amsterdam, and then you just say the distance to Vienna is like this, and the distance to New York is like this. So you have everything relative to each other. And
could you repeat that, Wolfgang? That's very important.
Yeah.
So you said, okay, normally you could be anywhere on the sphere. between North Pole and the South Pole.
Yes.
But now you say, okay, you have a point, Vienna and Amsterdam, and the only thing you measure is the distance between Amsterdam and Vienna.
Exactly. Yes.
But what do you do with that? What do you do with that distance?
So
how do you identify that you're either in Amsterdam or in Vienna?
Yes. So the readout, you basically do everything backwards. So you start in New York, and then it tells you, okay, you have to go 8,000 kilometers east. Then you're in Vienna, and then you have to go 808. I don't know how much to Amsterdam. So to say, you basically just go back. So this is what is called decoding. And decoding is actually a simple thing. So you just basically, if you build up these parities, you just remove them again. So this means the logical information of the position of Vienna, Amsterdam, and New York is always in the system. It's just represented in a different way. So imagine really two systems. One, classical computing, one stores the coordinates of Amsterdam, Vienna, and New York, and the other one stores the information of Amsterdam, so position of Amsterdam, and then the relative distance to Vienna and the relative distance to New York. So same information, just a different representation. One is what we call the parity, and the other one is, so to say, the standard model. And now the big advantage with distances, this doesn't help you anything. This will be just a different representation. But with quantum bits, what it does, it allows you to do operations that usually take 2 qubits on operations that only take 1 qubit. So for example, if you have to do an operation between Vienna and Amsterdam, let's say the operation would be that they have to move closer together. So I'm just making up an analogy now. So let's say they have to move closer together. Then if you would have them stored in 2 different bits, you would have to move both of them. So you would somehow have to move them like this. If you have the relative information stored, you can just say the relative information is smaller now. And you only touch 1 qubit. And this is just an analogy, but the idea is exactly this one, that single qubit operations on parity qubits are pair interactions in the standard quantum computing model. And now our operation, like the QFT, consists of a lot of pair interactions. Basically, all algorithms consist of an enormous amount of pair interactions. And now instead of really having to do them, you can act on single qubits to do them. And this is something that you can do in parallel and something that is much easier than a pair interaction. And this is, so to say, not so until very recently, this was a fundamental new construction and something that people are very fascinated about. But now we really proved that it gives a real world advantage on a real quantum computer by IBM running a real algorithm.
That's very cool. And thank you for the basic explanation. Now I get it much better. Wolfgang, what are the key lessons from your career on YOLF that shaped your personality and key beliefs?
So I think it's not a key story or something that really shaped me, but one thing that I often think about in the progress of filing the patent for the parity architecture. So when I did my PhD in Vienna, I invented a method that allows you to distinguish structures in 3 dimensions without knowing the structure. So you basically have points in space, and this algorithm allows you, or this method allows you to distinguish between different structures. And this was, I think it was even my very first paper, and is now my most cited paper. It's became a standard method in material science because it's very important to distinguish crystal structures there. And at that time, I would have never thought about filing a patent for that. So this was like, science, and we publish, of course, the science. And in this case, I was sitting in the PhD office where there were, I think, 8 people in one office, and the telephone rang So this was the time where we still had telephones. And it was Procter and Gamble on the other side. So they basically called me and asked, can we get a license for this method? And first of all, I didn't know who Procter and Gamble is. I only looked up afterwards that it's one of the largest companies. And I just said, there is, it's just a method that I published and it's open source. I can send you the code. And the lady said, "Oh, thank you," and hang up. This was indeed a little bit. I thought, okay, next time if I invent something really cool, I will make a patent.
And that's a very important lesson. And how does that help ParityQC?
Well, the patent is the starting point for the whole company. So if we wouldn't have this patent, there would be no company.
You paid very good attention to make sure that the patent was good and structured well, and that you got paid for your ideas.
Yeah,
I think that's a very powerful example, Wolfgang. Thank you for sharing. Magdalena, what were your key lessons that you learned during your career and your youth that shaped you as a personality?
Wolfgang had the fun story. I don't know if I have such a fun story, to be honest. When I think about where it came from, I have to say that this shaped me a lot. So my family has a lot of entrepreneurs in it. So this mindset that you have to actually work hard and do something to achieve something, that came very early on. And I was very lucky, to be honest, to be able to work with so many people that shaped the path until now. For example, in the previous company, I was able to work with a lot of genius people who founded companies and made mistakes, and I was able to actually be part of that. So I had a mental list that says, don't do this, don't do that, company, don't ever act like this. And
Magdalena, what were the 3 most important things you learned from that?
Culture in the company starts with the first employee. So Wolfgang and I thought a lot about how we want to actually raise the company and raise the people or shape the culture that we want to have in-house. And we see the benefits of it very well now. So we agreed on 2 things that are very important for hiring people. First of all, they have to be excellent in their field, but second of all, they have to be nice. And we see that the second part of it is as important as the first part. They are all team players. They all help each other. They support each other. And this is actually one of the key benefits that we both, I think, can appreciate from our past, which we took into the company.
And that's easy to be said, but what if people are underperforming? And what if somebody is not nice? Then how do you act then? Because if everything goes well, it is super easy. Everybody's happy. But with underperformers, things are much more difficult, and that really stress tests. I'm really focused on culture. I think culture eats strategy for breakfast. And culture is basically what determines a successful company to come up with the next idea. And culture is, how do we do things here? But how do you treat underperformers? And especially if people are not nice, how does that work within Parity?
So we of course had this. There are people that don't actually perform as the others do. And somehow they realize this, and then so far we had the experience that they then leave the company. There were not many cases, to be honest. So we have a very low fluctuation rate. But those people that underperformed usually leave the company because they see they can't actually reach the bar of the others. If those people don't realize themselves, while we're still executives, right, we have to sometimes let people go. That's just how the world works.
Okay. Thank you for explaining. On ParityQC, what is the mission of Parity?
So the mission is to enable hardware developers to build the best quantum computers using our architecture.
And how do you do that?
So the company is a architecture company, which means we are licensing to hardware developers. And the way we think about this is that we are the suppliers. We help hardware developers. So we are not in competition either with hardware nor with algorithmic developers. We are actually enabling the best to get the best out of the hardware. And the practicalities are somehow that there is I don't know, a handful of relevant hardware developers worldwide. And our goal is to work with all of them and become a standard. And in order to do this, we have to cover, of course, the different platforms. And we also have to give them an advantage. And so, for example, things like this world record are extremely important for us because, there is no ambiguities about it. No, there's no KPIs if you measure them like this or measure them like that. It's a full algorithm, fully performed on a quantum computer, and we have the world record. And so this is something that is, in my opinion, very convincing. And it allows us basically to work with as many as possible. So the idea is we don't want to, become part of another company. We don't want to be sold to one of the big ones. What we want to achieve is really to stay independent as a European company and provide our architecture to the whole world.
Okay, that's clear. What problems are you personally most obsessed with solving?
Personally, so one of the thousands of problems that come up every day. What I really don't like is inefficiency. So this is something that I really try to make it as minimal as possible. So whenever I come across something that doesn't work efficiently, I'm really obsessed with solving it, to be honest.
And you, Wolfgang, what problems do you want to solve at the moment where you're working on?
Yeah, so I'm of course very obsessed with quantum computing and architecture and the whole thing that we're doing in general. I think that's somehow an obvious obsession. What I also like in the role as founder of a company is working with people, and in particular trying to get not the best out of people, to let people bloom by themselves. So give them an environment which allows the company, which is a benefit for the company, but somehow, and I think Magdalena and myself, it's somehow exactly the same thinking. We want that people really bloom up in what they are doing. And because there's several benefits to it. The person itself benefits obviously by developing their own ideas, but also from a purely company perspective, we see it somehow, to us, it seems like the only scalable way for a company that people are self-interested in the company interests. So if you would make an old-fashioned structure, where basically ideas go all the way down to the working class, so to say, this is something that would never work in a high-tech company. It should be exactly the other way around. We want to hire, excellent people that everybody is a genius and everybody tries to, come up with something new. And this is something like an obsession, I would say, from both of us, that we try to bring people in this position, and that we are basically the soil on which everything can grow.
One question on the press release and the breakthrough. It sounds really interesting, but from the outside, how do we know it really works and it is credible? What is the conviction on it? So how can we judge that? So from most equity investors are not really technically detailed.
Mm-hmm.
It sounds very credible what you say, but why is it credible?
Yeah, that's an interesting question because we can, for example, for the algorithmic side. So I don't know how doubtful the investor is, but let me start with the algorithmic side. So the Quantum Fourier Transform is a textbook algorithm which you can analytically write down, and where you can basically, if you write it as a matrix, you can look at every single matrix element. And we have achieved not just an improvement of that, but we have also shown optimality for some cases of it. So for some quantum computers, the way, if you implement the quantum Fourier transform with the parity architecture, you cannot improve it anymore. So this means one part of the belief for the investor is a rigorous mathematical proof. So the algorithmic side, I would say, is, this is beyond any doubt. Now, if you say on the quantum computer, in some sense, okay, you cannot look into the quantum computer. In the end, you somehow have to trust it. Here, I would say for a conspiracy, we would have to conspire together with IBM, because we are doing this on the IBM quantum computer. So they would have to cheat together with us in the same way. And this is always my argument against conspiracy theorems, that if you need more than 10,000 people to do it, it's not possible. So,
okay, that's and how many people? You said okay, more than 10,000. How much were involved in this one?
well,
Two parties, but-
IBM. I mean, thousands of people are working at IBM now, and the quantum team is also huge. Yeah, I was saying this more as a joke. This is rigorous science, and I think this is peer reviewed. This is things that other people can test. This is also not coming out of the blue. As I said, it's the quantum processor. It takes literally 10,000 people to build these things. And on the algorithmic side, from our team, it's also a huge team. In science in general, things are always challenged.